You know, in AI, we're always chasing the next big thing, right? Bigger, more complex models. But what if? What if we've been running in the completely wrong direction? There's this new research paper out with a pretty wild claim that the key to the future of AI might have been just sitting on a shelf for the last 20 years. So let's dive in and see if they're onto something.
I mean, just think about it for a second. What if the future of AI was actually invented back in 1997? It sounds nuts, right? But that is the core idea we're digging into today. It's a total underdog story. And honestly, it kind of turns everything we thought we knew about AI progress on its head.
Okay, so to really get this comeback story, we've got to rewind the clock a bit. We're going back to the time before all the AI models you hear about today. For something like 20 years, the world of AI, especially for stuff like text or speech, sequential data, it was completely dominated by one type of model: recurrent neural networks. You probably know them as RNNs.
Yeah, for almost 2 decades, these models called LSTMs and GRUs, they were the undisputed champs. LSTMs, which came out way back in '97, were just fantastic at remembering things over long stretches. Like, imagine you're reading a huge paragraph. An LSTM could actually remember what the subject was from the very first sentence all the way to the end. It's pretty cool. Then GRUs came along as a simpler, faster version. Seriously, if you were doing anything with machine translation or text generation before 2017, these were your tools. They were the kings, no question about it.
But these kings had a huge, fatal flaw. They were slow. And I mean painfully slow. See, the way an RNN works is it has to process data one piece at a time, in order. The analogy here is perfect. It's like reading a book one single word at a time. You literally can't read the next word until you've finished the one you're on. And that created this massive bottleneck. Trying to train them on the giant data sets we have today, forget it. You'd be waiting forever.
And that slowness, well, that's what blew the doors wide open for a revolution. Because in 2017, everything changed. The entire AI world was completely upended by a new kind of model, a new architecture that solved this speed problem in a totally radical way.
Enter the transformer. You've heard of it. This is the architecture that powers literally everything you see today, from ChatGPT to all the crazy image generators. Its superpower? A little mechanism called self-attention. So instead of reading one word at a time, it can look at an entire sentence or even a whole paragraph all at once. And it figures out which words are most important to which other words, all at the same time. This means it can process information in parallel, like reading a whole page of a book at once instead of word by word. And that is the key reason we've had this insane explosion in AI.
But of course, there's a catch. As these transformer models got bigger and we started feeding them longer and longer pieces of text, a hidden weakness started to show, a crack in the armor. And it's a critical one that's become a huge new headache for the whole field.
And this brings us to the transformer's Achilles heel, something called quadratic complexity. It sounds complicated, but here's a really simple way to think about it. Imagine you're in a room and everyone has to shake hands with everyone else. If you double the number of people, the number of handshakes doesn't double. It goes way, way up. That's exactly what happens with transformers. If you double the length of the text you're feeding it, the amount of computation it needs doesn't just double, it quadruples. So for really long stuff, like trying to analyze a whole book or a giant codebase, it just becomes insanely expensive and inefficient.
So this is where our story gets really interesting. Researchers were getting super frustrated with the scaling problem in transformers. They started looking around for other options. And then this one paper came along and asked a brilliant, almost heretical question. What if the solution isn't some brand new, even more complex model? What if we could just radically simplify the old one?
And this is the absolute genius of the paper. It's basically a 3-step recipe for modernizing an old king. Step 1, you take a classic LSTM or GRU. Step 2, you perform some really clever surgery on it. You find the exact part that makes it slow and sequential, and you just remove it. That one little change unlocks everything, suddenly letting these old models train in parallel, just like a transformer. And then, for step 3, they just kept going. They stripped out even more stuff, creating these minimalist, super streamlined versions they call Min-LSTM and Min-GRU.
Okay, so now we have these revamped minimalist RNNs. In theory, they should be crazy fast. But the big question is, do they actually work? How do they perform in the real world? Well, it's time for a showdown. Let's put them up against the new kids on the block and see what happens.
First up, speed. And wow, just look at these results. They're absolutely staggering. That tall bar, that's the training time for a good old traditional RNN. And that tiny little sliver next to it, that's the minimal version. We're talking over 1,300 times faster to train on long sequences. That's not just a little better, that's a total game changer. It's a quantum leap.
Let's really let that number sink in for a second. 1,361 times faster. The paper puts it this way. A training run that would have taken a traditional LSTM over 3 years to finish can now be done by its new minimal version in just 1 day. I mean, come on, that completely rewrites the rulebook on what's even possible with these kinds of models.
Okay, but speed isn't everything, right? It's useless if the model isn't accurate. So how did they actually do? Well, check out this table. This is for a test called the selective copying task. You can think of it like asking the AI to find a needle in a haystack. It has to pull out very specific information from a really long and noisy chunk of data. And just look at these results. The minimal RNNs, the min-GRU and min-LSTM, they're performing right up there with Mamba, which is a state-of-the-art model today. And they absolutely demolish other modern models like Hyena. So yeah, they're not just fast, they are incredibly good.
So this brings us all the way back to that provocative title and the big question. We have these super simple, stripped-down versions of models from decades ago, and they're incredibly fast and incredibly powerful. So what does that mean for the future of AI? Were RNNs all we really needed this whole time?
The implications here are actually pretty profound. First off, it's a huge reminder that innovation isn't always about making things more complicated. Sometimes the biggest breakthroughs come from just making things simpler. And as AI models start using more and more energy, this kind of efficiency is absolutely critical. It also makes you wonder, what other amazing ideas for the future are just buried in the past, waiting to be rediscovered? And maybe the best part of all this, the paper says you can implement these models in just a few lines of code. That makes this kind of powerful AI way more accessible to everyone.
Honestly, this research really forces us to stop and think about the path we're on. It's such a great story, right? The old king, everyone thought he was obsolete, comes back and reclaims the throne. Not with more brute force, but with elegant simplicity. And it leaves us with this really cool question to chew on. What other old ideas from all over science are just sitting there, waiting for someone to take a fresh look and unlock their true potential?